Welcome everyone. Today I'll walk you through magnetic particle examination or MT, one of the most powerful NDT methods used in industrial inspection. Principles, applications, and inspection guidelines based on API 577 and ASME Section 5. We'll cover how it works, where and when it's applied, and the rules that guide its use. Please be informed, this summary is intended to simplify the content based on the presenter's interpretation. Magnetic particle examination or MT general overview, definition. Magnetic particle examination is a non-destructive method to find surface or near-surface defects in ferromagnetic materials, such as steel. Commonly used on welds, heat-affected zones, and back-gouged surfaces. Detects defects like cracks, laps, seams, laminations. In general, there are four main key steps of magnetic particle examination. Step 1 is magnetization. The test object is magnetized using either a permanent magnet or an electric current. Step 2 is application of magnetic particles. Fine ferromagnetic particles, dry or suspended in a liquid, are applied to the surface. Step 3 is detection. If there's a flaw, like a crack, it will interrupt the magnetic field, causing leakage. The particles gather at the leakage field, forming a visible indication, surface defects showing sharp and clear indications, and subsurface defects showing fuzzy indications. And step 4 is interpretation or inspection. The indications are visually interpreted under white light or UV light. For fluorescent particles, best results when magnetic flux lines are perpendicular to the defect. There are two inspections commonly in used are parallel and perpendicular to weld for full coverage. In general, the advantages of magnetic particle examination: quick and relatively easy to perform the examination or testing. It has highly sensitive to surface cracks. MT given immediate results. And MT tools is portable equipment, and in general, the limitations of magnetic particle examination, MT only works on ferromagnetic materials. Surface are to inspect must be accessible and clean. And MT requires proper magnetization and demagnetization. Magnetic particle testing or MT is widely used for weld inspections because it's highly effective at detecting surface breaking and slightly subsurface defects in ferromagnetic welds. Common weld defects detected by MT includes surface cracks, lack of fusion, undercuts, porosity, if near surface, slag inclusions. Why MT is preferred for welds? MT is fast and cost-effective. High sensitivity to surface breaking defects. And portable equipment suitable for field inspections. Here's how it's applied: magnetic particle examination or MT specifically for welds. Step number 1 is surface preparation. Its goal is to ensure the weld area is clean and free of contaminants. Why it matters? Because dirt, oil, paint, or rust can block magnetic particles from reaching flaws. Tools can be used for surface preparation but not limited to wire brushes, solvents and grinders. Step number 2 is magnetization. The goal of this magnetization is to create a magnetic field in the weld area. Methods used for magnetizing are: the first method is yoke. It is portable and ideal for spot checks. The second method is prods. It is for larger areas. And the third method is coils or central conductors. It is for circular magnetization. Key point of magnetization is field direction should be perpendicular to expected defect orientation. Step number 3 is application of magnetic particles. Types of MT application are: dry particles, used in daylight or rough surfaces, and wet suspension, more sensitive, often fluorescent for UV inspection. Application timing, during or immediately after magnetization. Step number 4 is inspection. Use lighting to inspect. White light, for visible particles, and UV light, for fluorescent particles, requires darkened area. What to look or inspect for: inspect the particle buildup indicating cracks, lack of fusion, or other defects. Step number 5 is demagnetization. Why demagnetization's needed? Residual magnetism can interfere with equipment or future processes. Its methods commonly AC demagnetizers, reversing DC current, or heating. Step number 6 is documentation, includes type and location of defects. Acceptance criteria based on standards such as ASME, AWS. Inspector's name, date, and method used. There are two main key techniques used in magnetic particle examination. Technique number 1 is dry magnetic particles commonly used outdoors. This technique has lower sensitivity. And wet magnetic particles technique commonly used indoors and has higher sensitivity. And technique number 2 is wet fluorescent magnetic particle testing or WFMT. It uses black light and has higher sensitivity. Let's get deep dive into dry versus wet magnetic particles technique. For dry magnetic particles or dry MT technique, its form is finely ground ferromagnetic powder. Application of this dry MT is sprinkled or blown onto the surface after magnetization. The visibility of this dry MT is typically colored, red, yellow, black, for contrast under white light. And the sensitivity of this dry MT is lower than wet particles, but effective on rough surfaces or in outdoor conditions. The advantages of dry magnetic particles or dry MT technique are: no need for carrier fluid, good for high-temperature surfaces, portable and easy to use in field conditions. And the limitations of dry magnetic particles or dry MT technique are: less sensitive to fine or shallow defects, can be difficult to apply uniformly, not ideal for smooth or polished surfaces. Now let's go through wet magnetic particles or wet MT technique. Wet MT form is ferromagnetic particles suspended in a liquid carrier, usually water or oil. The application of this wet MT is sprayed or flowed over the surface during or after magnetization. The visibility of this wet MT can be visible, colored, or fluorescent. And the sensitivity of this dry MT is higher than dry particles due to better mobility and surface coverage. The advantages of wet magnetic particles or wet MT technique are: uniform coverage, better sensitivity to fine cracks, easier to apply on smooth surfaces. And the limitations of wet magnetic particles or wet MT technique are: requires containment and cleanup, not suitable for high-temperature surfaces. Carrier fluid must be compatible with the material. Next is technique number 2 called wet fluorescent magnetic particle testing or WFMT. Wet fluorescent magnetic particle testing is a high-sensitivity method using fluorescent particles suspended in a liquid carrier. Inspection is performed under UV, blacklight, in a darkened environment. Next is technique number 2 called wet fluorescent magnetic particle testing or WFMT. Process step when conducting wet fluorescent magnetic particle testing. Step number 1 is surface preparation. Clean and dry the surface thoroughly. Step number 2 is magnetization. Apply magnetic field using yoke, prods, or coils. Step number 3 is application of fluorescent particles. Spray or flow the suspension over the surface. Step number 4 is inspection under UV light. Use a UVA lamp, typically 365 nanometers wavelength. Inspect in a dark room or shaded area to enhance visibility. And if there is any defect shown, we will see the fluorescent particles glow brightly at defect sites. Step number 5 is interpretation. Look for glowing indications that reveal cracks, porosity, or other discontinuities. And last step is post-inspection. Clean the part and demagnetize if necessary. The advantages of wet fluorescent magnetic particle testing are: extremely sensitive to fine and shallow surface defects, high contrast between indications and background, ideal for critical components in aerospace, nuclear, and pressure vessel industries. And the limitations of wet fluorescent magnetic particle testing are: requires controlled lighting conditions, UV lamps must be regularly checked for intensity and wavelength, fluorescent particles and carrier fluids must be handled with care, some may be hazardous, not suitable for field use in bright environments. Based on API 577 and ASME Section 5, Article 7, here is a very detailed explanation of the code requirements for magnetic particle examination or MT. Number 1 is procedure details. MT must be performed according to a written procedure that includes technique use such as yoke, coil, prod, write-in procedure, the type of particles, dry, wet visible, wet fluorescent, write-in procedure, the magnetization method, continuous, residual, true continuous, write-in procedure, the equipment and calibration requirements, write-in procedure, the acceptance criteria and evaluation method, and write-in procedure any change in essential variables, for example technique, particle type, current type requires procedure requalification. Code requirement number 2 is continuous method. Continuous technique. Magnetic particles are applied while the magnetizing current is on. Inspection may continue with the current off, but particles must be applied during active magnetization. Ensures maximum sensitivity to surface breaking defects. Code requirement number 3 is approved magnetization techniques. ASME Section 5 recognizes 4 methods, includes, yoke method or AC/DC, prod method, coil or cable wrap method, and central conductor method. Techniques may use, included, AC, DC, FWDC, HWDC currents, and the other method permitted by the code are true continuous, and residual magnetization methods. Code requirement number 4 is equipment calibration. Equipment must be calibrated every 6 months or when accuracy is questioned. The equipment to be calibrated includes, yokes, must lift 10 pounds test block at max leg spacing. Light meters, white and UV. Gauss meters. Magnetizing units. And centrifuge tubes for particle concentration. Calibration records must be traceable and documented. Code requirement number 5 is 2 perpendicular inspections. Each area must be inspected twice, with magnetization 90 degrees apart, ensures detection of defects in any orientation. Overlapping inspection areas are required for full coverage. Code requirement number 6 is surface temperature limits. Part surface must not exceed 135 degrees Fahrenheit or 57 degrees Celsius. Solution temperature must not exceed 110 degrees Fahrenheit or 43 degrees Celsius. Temperature difference between solution and part must be within more or less than 25 degrees Fahrenheit or 14 degrees Celsius. High temperatures can affect particle mobility and visibility. Code requirement number 7 is magnetization current control. Magnetizing current must be controlled and verified. Use of amperage meters and field indicators such as pi gauge, Castrol strip is required. For coils, current and number of turns must meet ampere turn or at requirements. Polarity checks must be performed to ensure field reinforcement. Code requirement number 8 is indication evaluation per code. Only relevant indications are evaluated, includes, for linear indication, evaluate the length must be greater than 3 times width. And for rounded indication, evaluate the circular or elliptical shape. Indications that greater than 1/16 inch or 1.6 mm are considered relevant. False indications such as from rough surfaces or permeability changes must be re-examined. Acceptance criteria are based on ASME Section 8, API 650, or project-specific standards. Code requirement number 9 is demagnetization after test. Demagnetization required if residual magnetism interferes with further processing and affects equipment function. Demagnetization methods include AC demagnetization or gradual withdrawal, reversing DC current, and thermal demagnetization above Curie point. Residual field must be measured and reduced to acceptable levels, typically less than 2 Gauss. Code requirement number 10 is minimum lighting requirements. Visible MT minimum 100-foot candles or 1076 lux at surface, lightning for fluorescent MT or WFMT as per the following. For UVA intensity greater than or equal to 1000 W/cm superscript 2 at 15 inches. Darkened area required. Ambient light less than or equal to 2-foot candles or 21.5 lux. Eye adaptation should be conducted 5 minutes before inspection, and no photosensitive lenses allowed during UV inspection. Based on the details from ASME Section 5 and referenced in API 577, here are the 5 magnetization methods used in magnetic particle examination or MT. Here we go through in depth. Method number 1 is prod method. This method is a direct magnetization technique where current is passed through 2 contact prods placed on the surface of the test object. Field type of this method is to produces a circular magnetic field between the prods. This method best applied for localized areas such as welds or small components. The advantages of this prod method includes simple and portable and effective for detecting defects between the prods, and the limitations of this prod method includes risk of arcing or burning the surface. Limited to small areas. And the best practice of this prod method is to ensure good contact and avoid excessive current to prevent surface damage. Magnetization method number 2 is longitudinal magnetization method. This method is to magnetizing current flows parallel to the length of the part, creating a longitudinal magnetic field. field type of this method is magnetic lines run along the axis of the component. Application of this method is ideal for detecting transverse cracks, perpendicular to the part's length. The advantages of longitudinal magnetization method. This method is good for long components like shafts or pipes, and the limitations of longitudinal magnetization method. This method may miss longitudinal defects unless reoriented. The best practice of this method is use in combination with circular magnetization for full coverage. Magnetization method number 3 is circular magnetization method. The current in the method is passed through the part, generating a circular magnetic field around the cross-section. Field type of this method encircles the part's diameter. Application of this method effective for detecting longitudinal cracks, parallel to the part's length. The advantages of circular magnetization method is high sensitivity to axial defects. The limitations of circular magnetization method is requires direct electrical contact. And it is not suitable for non-conductive coatings. The best practice of this method, it is use clamps or central conductors to ensure uniform current flow. Magnetization method number 4 is yoke method. It uses an electromagnetic yoke to induce a magnetic field between its poles. Field type of this method is for localized longitudinal field between the legs of the yoke. Application of this method is most common method for weld inspection and field work. The advantages of yoke method. It is portable and easy to use. And no direct current through the part. The limitations of yoke method is limited penetration depth. And requires multiple orientations for full coverage. Best practice of this method is to inspect in 2 perpendicular directions to detect all flaw orientations. Magnetization method number 5 is multidirectional magnetization method. It combines 2 or more magnetization directions simultaneously or sequentially. Field type of this method is complex field covering multiple orientations. Application of this method is to used in stationary equipment for thorough inspection of complex geometries. The advantages of multidirectional magnetization method able to detect flaws in all directions in a single setup. And has a high reliability. The limitations of multidirectional magnetization method. It requires specialized equipment and not portable. Best practice of this method is ideal for critical components in aerospace, automotive, and pressure vessels. Magnetization method selection tips. Use yoke method for quick field inspections of welds. Use prod method when access is limited and localized testing is needed. Use circular or longitudinal magnetization for full body inspections of cylindrical parts. Use multidirectional magnetization for high reliability applications where defect orientation is unknown. Demagnetization is an important step after magnetic particle testing or MT, especially for weld inspections, to ensure that residual magnetism does not interfere with equipment operation, machining, or further testing. Here's a detailed explanation of the main demagnetization methods. Number 1 is AC demagnetization or alternating current. How it works: alternating current is passed through a coil or yoke, and the part is slowly withdrawn from the magnetic field. AC demagnetization effect: the alternating magnetic field gradually reduces the residual magnetism to near zero. AC demagnetization best for small to medium-sized parts. The advantages of AC demagnetization method is simple and effective, and the limitation of AC demagnetization method is less effective for deep-seated magnetism or large parts. Demagnetization method number 2 is reversing DC demagnetization or direct current. How it works: direct current is applied in alternating directions with decreasing intensity. DC demagnetization effect: this gradually neutralizes the magnetic domains. DC demagnetization best for large parts or parts with deep residual magnetism. The advantages of DC demagnetization method is more thorough than AC for deep magnetism, and the limitation of DC demagnetization method is requires controlled equipment and more time. Demagnetization method number 3 is mechanical movement through AC field. How it works: the part is physically moved through an AC coil or field, then slowly withdrawn. Effect of AC field method is the changing field orientation helps randomize and cancel magnetic domains. AC field method best for long parts like shafts or pipes. The advantages of mechanical movement through AC field is effective for elongated components, and the limitation of mechanical movement through AC field is requires space and handling equipment. Demagnetization method number 4 is thermal demagnetization. How it works: the part is heated above its Curie temperature, the point at which it loses magnetic properties, then cooled in a non-magnetic environment. Effect of this method is resets the magnetic domains. This method best for parts that can tolerate high heat. The advantages of this method is very effective. And the limitation of this method is not suitable for heat-sensitive materials or precision parts. Demagnetization method number 5 is manual demagnetization, handheld tools. How it works: it is using portable AC demagnetizers or yokes. The inspector manually sweeps the tool over the part. Effect of this method is, it reduces residual magnetism in localized areas. This method best for field use or small components. The advantages of this method is convenient and portable. The limitations of this method is may not fully demagnetize large or complex parts. How to verify demagnetization: use a Gauss meter or magnetic field indicator to check residual magnetism. Acceptable residual field levels depend on the application, often less than 2 Gauss for sensitive equipment. Flux direction indicator, pi gauge, as referenced in API 577. The pi gauge, also known as a magnetic flux direction indicator, is a specialized tool used in magnetic particle examination or MT to verify the direction of magnetic flux on a surface. This is crucial because defect detection is most effective when the magnetic field is perpendicular to the defect. Let's get deep explanation of the pi gauge. Construction of pi gauge. Pi gauge made from 8 ferrous segments, low carbon steel, brazed together into a circular disc. The segments of pi gauge are separated by non-ferromagnetic material, creating artificial discontinuities. These discontinuities radiate outward like slices of a pie, hence the name. Mounted on a non-ferrous handle with a pivot for easy placement. What is the function of pi gauge? The pi gauge does not measure field strength, but it reveals the direction of magnetic flux. When placed on a magnetized surface and magnetic particles are applied, indications appear along the artificial discontinuities. Strong indications form perpendicular to the magnetic flux, weak or no indications form parallel to the flux. This allows inspectors to confirm whether the magnetic field orientation is suitable for detecting defects in the desired direction. How to use the pi gauge. Step number 1 is, place the pi gauge flat on the surface with the pi sections facing down. Step number 2 is, magnetize the surface using a yoke, prods, or other magnetization method. Step number 3 is, apply dry magnetic particles, typically used with pi gauges. Step number 4 is, observe the indications, strong, well-defined lines. It means flux is perpendicular to those segments. Weak or no lines, it means flux is parallel to those segments. Step number 5 is, adjust magnetization direction if needed to optimize defect detection. When, what and how to apply pi gauge. Pi gauge commonly used in yoke inspections. Pi gauge ideal for flat surfaces like weldments and steel castings. Pi gauge helps ensure proper field orientation before applying magnetic particles. Limitations of the pi gauge. While the pi gauge is a useful tool for verifying magnetic flux direction, it has several limitations that inspectors must be aware of. Limitation number 1 is, pi gauge not suitable for wet MT. The pi gauge is designed for dry particle applications. Wet particles, especially fluorescent, may not adhere well to the gauge's surface or show clear indications. Limitation number 2 is, pi gauge limited to flat surfaces. It must sit flush on the surface to work properly. Not effective on curved, irregular, or complex geometries. Limitation number 3 is, pi gauge cannot measure field strength. It only shows flux direction, not intensity. For field strength, tools like Hall effect probes or Gauss meters are required. Limitation number 4 is, pi gauge for artificial discontinuities only. The indications seen are not real defects, but simulated ones. It cannot detect actual flaws in the test object. Limitation number 5 is, pi gauge residual magnetism. The gauge can become magnetized during use. Must be demagnetized before reuse to avoid false indications. Limitation number 1 is, pi gauge limited coverage, only shows flux direction at the specific point of placement. Multiple placements may be needed for large surfaces. Thank you.